We can see the structure of this network in this picture here. So we have our input sample, we'll have our input layer that will take this input sample and then it will distribute to n hidden nodes with weights, and each node will have a bias and activation function, and then there will be followed by the output layer that in our case it just will add all the inputs from the hidden nodes with weights but without any activation function. So we will define our 3-layer neural network with the following class in PyTorch. So we are defining the number of nodes that we want to use. So we are using 10 nodes. Then it will be a 2-layer fully connected layer with one input time value, and then hidden layers that has capital N nodes and one output function value. So this is what we're doing. We're defining this class called LinNet, and then we're having here a first layer, and it will be linear layer. We have features equals to 1, output input features equals 1, output features equals the number of nodes, and we are setting bias equals true. You're defining another layer, layer 2, that has the input features is the number of nodes that we defined earlier, and the output features both equals to 1. Here we are defining our activation function. We are going to use the sigmoid. At the forward method, we are putting the network together. So here we are taking the output from the first layer, layer 1. Then there is the activation function acting after the first layer, and we get this second layer, and then we are returning the output of the second layer. So we see that there is no activation function in the output. So after we define the architecture of our network, we will first generate the training and validation set, then we will instantiate and initialize the model, and the model will be initialized with random weight values. So here we are creating our training set, and like we explained before, so we have our input generates n time steps for x, and then we are reshaping, so we have the last dimension for our signal and the first dimension for the batch. Then we are creating the target, that here is a noisy function value, so it's sine function plus normally distributed random values, and this is what we are doing here. And we are also reshaping our target. This is our training set. For our validation set to test generalization with new noise, and we are also generating for extrapolation, we are generating 2 times capital N time steps for x, and this is what we are doing here for our validation set input, so x validation, and the validation target is y validation. Here we are creating our network object, and we are calling it model. So before training, we can take a look at the weights. So these are the weights in the initialization of the model, so it's before training. And then we can take a look at also the prediction before training. At this point, we will define the loss function and define the optimizer we are going to use. So we are going to use the mean squared error loss, and this is what we're doing here. And we are going to use the Adam optimizer, and here is where training in fact takes place. So this is where the optimization occurs, and we are using 10,000 epochs for our training. Here the model produces the prediction output. At this point, the prediction and the target are compared by the loss. We are printing the current loss value for every 1,000 epochs. Here we are calling the 0 grad, so the optimizer set previous gradients to 0. Here we use it for so that the optimizer will compute new gradients and the optimizer to update the weights. So this is where the training takes part. After that, we can compute the resulting loss value on the training set and the validation set, and we can plot the obtained learned function in comparison to the noisy target function for training and for validation. So we see that for plotting we need NumPy arrays, so we will have to convert from PyTorch tensors to NumPy arrays, and we can use this NumPy here to do this conversion. And here we are now making the predictions based on the obtained weights. Here we are calculating the loss, so we can print, and we will plot the predictions. We will plot the target, so we will compare the training target with the prediction output, and it will be in our plot called results. And we will do this for the training and for the validation and see what happens. So this is the basic structure what we are going to use, and here is our code. So we are importing PyTorch, we are importing matplotlib pyplot for plotting. So we're defining n equals to 40, so this will be the number of samples in our signal, and we are going to use 10 nodes in the hidden layer. Here again I'm just showing how we define the structure of the architecture of our network, and we define and initialize the layers. We define the forward method, so we are putting the network together. Here we are creating the inputs and targets like we explained before. Here we create the network object. We see how things look before training, then we train, then we see how things look after training. So when we run these cells, we see the number of input samples is 40, number of nodes is 10. We see the shapes of our tensors. Here we see the initial weights. So this is the before training, so the weights here are initialized randomly. Then we start optimizing, and we are printing for every 1000 epoch, and this is the final loss on the training set and the final loss on the validation set. So we see that part of the printouts are the initial weights before the optimization that we see here. They are randomly initialized and they are obtained with these lines here, and it shows a dictionary of weights and biases. So this is what we see, the weights, and we see some biases. So observe the data format. The first dictionary entry is a layer 1.0.weight, which is a two-dimensional tensor or matrix, and this represents the matrix A of the first linear layer of our network. So you can take a look at the documentation of PyTorch for linear layers and take a look on how it works. Remember that the equation was given by here. So y is the output, x the input. We have this matrix transposed A plus B. In our case, x consists of just one feature. It's a one-dimensional, and we have n output features or nodes. So you can compare with the network picture in the first part, and A, this matrix A must have one column of n entries, which is what we observe. After that, we see layer 1 bias, which is the bias vector with n entries, or one bias entry for each output node. And then the layer 2 weight, which are the weights for the next layer, which has capital N input features and one output features. So this is the approximated function value. Hence, it has one row with capital N elements. And finally, we have the bias for this layer, and it has only one entry since it only contains one node. So that's what we see here. We have the weights for the first layer, the bias for the first layer, the weights for the second layer, and the bias for the second layer. Then the optimization runs and we obtain the losses. So this is what we had after we ran our program here. We got these outputs here, the losses for every 1000 epochs. So the loss on the validation set is somewhat higher than from the training, but less than a factor of 2, which is not too bad. If we increase the number of nodes to 80 or 100, we will observe that the loss on the training set will go down, but the loss on the validation set maybe go up, and this is a sign of overfitting. Also, we can try with different activation functions, like the leaky ReLU, for the case of, for example, 80 nodes, and it leads to a similar loss. And then you can try the ReLU, and you'll find that the optimizer has a much harder time to find a good solution because of the vanishing gradients of the ReLU activation function for negative inputs. So now we see the function plot for the 10 node training set, and this is what we have here. So we see our training target, which is in blue here, and it is a sine plus noise, and then we see our prediction output. We see that we get indeed a smooth version of the training set, which means our network is somewhat robust against noise on the training set. For the validation set, we have now, again, in blue is the validation target, which is now is 2 cycles of a sine wave with noise, and we have the prediction output, but we see that we have a good interpolation on the capital X range of the training set, but the extrapolation beyond this training set is not working. So we see that we start getting a sine wave, but at this point it just goes completely different. So the resulting function from the network is the sum of the functions of all the nodes. And to see the functions of the individual nodes, we can just keep their weight unchanged and set the others to 0 and plot the resulting function. And for that, we can mask with zeros for the weights of layer 2, except for one node, and then plot the function. So we can repeat this for every node in a for loop, and this way we can see the individual the functions of the individual nodes. And this is what we are doing at this part here in these 4 nodes. So for each node we are doing this weight mask, so we mask with all zeros for the output layer except 1. We leave 1 node unchanged, and then we see and we will plot. So these are the basis functions of the network. So we have for node 0, for node 1, for node 2, and so on. So each node has its individual contribution. Here we see that the activation function of each node is fit with bias and weight to different parts of the target function, since the activation function is only fitted over the training range. They all become flat after that, and hence their sum also becomes constant. And this is what we're observing here. So they all become flat, and then their sum will become constant.